stochastic localization. So this morning we saw that when you have a probability measure on Rn, you can decompose it along needles, and if your probability measure is log concave, you can decompose it along log concave needles. So you can sort of write your measure as an average of needles, and here I will write my measure as an average of Gaussian perturbation of my measure. So this is something that was introduced by Eldan in 14, I think. And so the idea, the basic idea is that, so I will start with mu. You multiply by some Gaussian factor, so of the form x some constant plus maybe over 2 here. With so I will choose this direction of the Gaussian by which I multiply. I will choose it at random, and I will choose it at random and such so that in average I have done nothing. So this thing is 1. Okay. And what I will do is that, and then repeat it. And what I will do is that instead of doing it in discrete time, like I'm describing now, I will do it in continuous time. This thing, yeah, so that this thing in average is 1. So so this is a random. I want the expectation of this guy to be 1. If you want. And only theta. No, theta will be. I will explain how I choose theta. I'm just saying that I will somehow I will multiply my measure with which I start by some random Gaussian, but the random density is will be 1 in average. Okay. So let me try to do it a bit more okay. Let's dive into a bit more the details. So let's start. So formally, and then I'll do a more serious construction. So I will start with WT, which is standard Brownian motion. And I will consider the following system of equation. So I will start with P0 of x is 1, Pt of x. So the derivative along time will be Pt of x times x minus at dwt, where at is integral on Rn of x Pt of x mu of dx divided by integral on Rn pt of x mu of dx. Okay. So here, what I have is a sort of a system of a stochastic differential equation, but an infinite system because I have one equation for every x on Rn. And these equations are all coupled together by the fact that this AT here, it depends on all the PTX simultaneously. So it's not at all clear from this picture that such a thing should exist. But let's forget about this for now. And let's try to play around with this definition. Okay. Think of PT, well, x dot PT as a random density. And okay, what I want to stress is that first of all, so okay, maybe the first condition that you can extract from this is that if you formally, if we exchange the Ito derivative with integration, we see that the derivative of the integral of pt of x mu of dx is so it will be integral x minus at pt of x mu of dx times dwt. And this is 0 by definition of at. So this means that almost surely this stays at 1. So pt of x mu of dx is a random probability measure. Let me give it a name, so call it mu t. So the second point is that somehow the equation that you have for pt, you can solve it. Because if you look at d of log pt, then you will get this first term. And then you have Ito's term. That comes from the second derivative of the log. And this does not depend on pt anymore, so this is what I mean by solving. So pt of x, okay, you can write it as the integral of all this. X, the integral of all this. And if you look at this expression as a function of x, it's a relatively simple function of x, okay? Because you have some constant terms, you have some linear terms in x, and you have a quadratic term, okay? So some function, some constant term that depends on t but not on x, some linear term, and the term that is quadratic, let me write it explicitly, is just t over 2 x squared. All right? Okay, so mu t, which is pt of x d mu, so d mu t, which is pt of x, is a Gaussian perturbation of mu t. Okay, the linear part theta t is random, but the quadratic term is just t x squared over 2. In particular, this is deterministic. Okay? Of mu, sorry. Merci. So, in particular, if mu is log concave, okay, so log concave, recall this means mu has a potential which is E minus V with V convex. Then mu t. Okay, so is E minus Vt of x dx with Vt that is more convex than V, because you've gained some convexity from the Gaussian term, which is t squared. So with, if you want Hessian of Vt rather than t times identity, and this would be almost surely. And such a measure, I will call it T uniformly log concave. T uniformly log concave. C'est pas le bon. Okay, the third observation from the definition of PT is that in average, it's still very formal at this stage, but PT of x, yes. So theta t is some random process. I can write a formula in terms of AT and WT, but I didn't write it. All I wanted to emphasize in this formula is like the dependence on x is just some Gaussian factor. So AT, you still have the formula over there for AT. So you see AT is the barycenter of mu t. Non. J'ai écrit un AT of x quelque part. Non, ok. So in all this that I wrote here, so CT, theta t, AT, they don't depend on x, but they depend on the randomness. They are random processes. And the third thing is that PT, so okay, the derivative of PT is some martingale increment. Okay. So in particular, expectation Pt of x is constant over time. So it's just P0 of x, which is 1. So my random probability measure mu t on average is just mu. So here you can think of it as a, maybe you can make a connection with what Boas did this morning. So he wrote mu as some average of needles. Here I write mu as some average of Gaussian perturbations of mu. Okay? Okay, so this allows to write mu as an average of Gaussian perturbation of mu. And somehow what you will see later on today and tomorrow is that because we construct it by solving a certain stochastic differential equation, you can somehow control the evolution of mu t using stochastic calculus. And this is something that I will use a lot. So now, as I said, it's not clear at all why such a process should exist, because it's really not a standard stochastic differential equation. First of all, you have infinitely many equations, and they're all coupled together, so this does not fit at all at least the classical theory. So I should say some word about how to construct it. So here I will, I won't do it like Ronan Eldan was doing it. So this was introduced by, Eldan 14, and then there were many like developments around this. So maybe Livan Pala. Chen. 21, 22, 21, I don't remember. Okay, I will give you somewhat different construction than what is considered in this series of papers. It's pretty much inspired by another paper by Klartag, joint with Peterman. Maybe a bit before that. Yeah, all these dates are approximative. But slightly different still. Okay. Now, start with n-dimensional Brownian motion standard, which I will call theta t. This is a very odd name for a Brownian motion, but you'll see why. Observe that x, so for any fixed x, for fixed x, this quantity x dot theta t. Theta t is a Brownian motion, so it's a martingale. If you take the exponential, this will grow. This will be a sub-martingale, so you need to compensate. And to compensate, you need to subtract t x squared over 2 is a martingale. Okay, so so by Fubini, so if f is some test function, if I integrate this will be still a martingale, still be a martingale. Integral on Rn f of x exp x dot theta t minus t over 2 x squared d mu is still a martingale. So let me give a name to this guy. N sub t is a martingale. Okay, so far so good. En fait, descendre celui-là aussi. All right. Moi, j'ai toujours le même problème. Donc. Mm-hmm. Okay. This is Ito's formula. Okay, so I'm afraid stochastic calculus is like a prerequisite here. I don't have time to. So you can think of it as a. So in any case, when you. So this is stochastic calculus. So you have the usual calculus. But since dWt is like some Gaussian jump with whose size is about square root t, if you want to go to something that is order dt, you have to go to the second order term. Okay, and the second order term is half Laplacian f at wt dt, and okay, that's Ito's formula. And okay, so so nt, which is so integral f x exp x dot theta t t x squared d mu is a martingale. So now I will do something that looks a bit stupid, which is, so I have perturbed my measure mu by some Gaussian factor, so I will somehow normalize. Okay, so I will write it as okay, the same thing. Okay, so I want a probability measure. So I want to perturb by some probability measure. So I will divide by okay, so I renormalize to make it a probability measure. And here this looks idiotic, but okay, and now I will interpret those two terms, or the two factors, in two different ways. No, there is no CT. here. It's really heavy.
So why didn't the denominator is 1?
No, the denominator is not 1. Okay. Why? Maybe I tried to win some time, but maybe this was a waste of time.
What equals?
This is equal to this. Okay, I did something so stupid that... okay, I divide and multiply by this. Okay, so I did nothing. I mean, this you should agree. Maybe not the rest, but... okay, so for now, I just want to give names to things. So this I will call it integral of f d mu t. And by definition, mu t is a probability measure. Now, this normalization constant okay? And now I will interpret it as a change of measure. A change of the change of probability space, if you want. What do I mean by that? Yes, constant as far as x is concerned. In x. Yeah, what I mean here is that if like omega is fixed, random, and I look at this expression, so I divide by the integral of this to have a probability measure, and then remultiply. And that this term here that doesn't depend on x, it's still random, but it doesn't depend on x, I will interpret as a change in my probability space. So set d sub t equals okay. So again, d sub t is a martingale. It's positive. Okay. It's a martingale if you want, because if you fix x, this expression here is a martingale. So if you integrate with respect to it's still a martingale. Okay. It's positive, and the expectation of dt is so d naught, and d naught is 1. Sorry? Yeah, also, yeah, the answer is yes. You can think of it like the expectation is constant for now. And what happens now is, okay, so fix some time horizon capital T. And I will change the probability measure by somehow tilting it with this guy. And define some new probability measure But here, it's not a probability measure on Rn. It's the probability measure on my ambient probability space. Okay, my Brownian motion is defined on some probability space. I don't know, omega f p. And now, what I mean new probability measure is I will change this p. Okay. So q of d omega. Well, if you want dq is d capital T dp. Yeah, P contains all the randomness. So at the very beginning, I said let theta be some Brownian motion. So Brownian motion defined on some probability space. That's P, and there is no other randomness. Okay, there's a fact which I can leave as an exercise. Which is MT is P martingale. So martingale for P. If only if, sorry, it's a Q martingale. MT dt is a P martingale. And here I have fixed my time horizon for so it's on 0 t. Okay, so since nt, which was integral f of x dot theta t minus x squared over 2 d mu. So you remember this was nt, and this was integral of f of x d mu t. Times dt was P martingale. So P martingale, I hope the notation clear. It means a martingale under the probability space P. So this, okay, from this fact, you get that this process is a martingale under Q. Ok, oui. Oh non, pas les filtrations. Quoi. No, we can. No, don't bother with filtration. It's. No, the say the. Yeah, the filtration. Ah, je crois que tu me demandes s'il fallait qu'elle soit continue à droite et tout. Non, ok. Okay, so yeah, martingale is with respect to some filtration, so I don't change the filtration. The filtration is the same. A good question. Sorry. Okay, So this process here, MT, is a Q martingale. So for any test function f. So in a sense, this is what I mean by mu t is a martingale. So mu t is a measure valued martingale, and this is under Q. So you see, I've started constructing what I want, because under this new measure Q, this is indeed a martingale, and this mu t, it indeed has like the required property that I had. It's the perturbation of mu by some Gaussian factor. Okay. Now there is one. I mean, if you just, I don't want to stop here because later on I will have to do some computation, and to do some computation, I need to know what is the Ito derivative of this martingale. Okay, so what is the Ito derivative of MT? So if you think about it for a minute, this means if you start with some martingale or some local martingale or some semi-martingale, if you know what it means, and you change the probability measure, then what is your new decomposition? Are you still a semi-martingale, and what is the decomposition? Okay, this is a legitimate question, which has a very classical answer, and this is called Girsanov change of measure formula. So we need Girsanov. Okay, I'll say a few words about this thing, Girsanov. So what is Girsanov? So you're in the situation above. So Q is dt dp. If x is a p martingale, define x tilde to be x minus, so at time t, integral from 0 to t d xd divided by ds. Then the following, okay, you don't really need, you don't need martingale. Let me be a big weight. Define x tilde. So here this is quadratic variation. Of the processes. Oh, it's right, the quadratic covariation, sorry. And then the statement is that x is a p martingale if only if x tilde is a p martingale Q. And there is another statement to it, is that this operation, like you perturb your process by something that is absolutely continuous, so you don't perturb the quadratic variation. So these two processes, they have the same quadratic variation, which means in particular that if the process you start, like a Brownian motion is characterized by its quadratic variation, which is just T. So if you start with a Brownian motion here it will be also a Brownian motion. Okay, so moreover, if X is a P Brownian motion, X tilde is a Q Brownian motion. Sorry?
The process B3 is exactly what we had before?
Yeah, so in a context where I'm in a so dt, I will apply it to this dt that I had before, but you can think as a general statement. What is dt? That's the question? Yes, okay. So dt is a martingale, positive expression. Okay, if you want, dt is expectation in condition on ft.
It's P and EP.
Yes, under P. I have not changed at this stage. C'est ça? Okay, so again, I have my probability measure, I multiply by some density, then I look at the martingale associated to this density, then I construct this weird object, and I'm saying that this guy is exactly like this compensation here is exactly what will compensate for the change of measure. Okay, let me give so this is a very classical tool in stochastic calculus. Let me give a very brief sketch of why this is true. Je ne l'ai pas dit à l'envers d'ailleurs. Hein. Okay, let me check on my notes because I always get confused. Non, je crois que c'est bon. Okay, so proof. So X tilde Q martingale is equivalent by my fight that is somewhere like behind this board. X tilde D P martingale. So all I need to check is that this guy is a P martingale under, and then I can do Ito, or if you want like integration by parts, Ito integration by part. Which tell you that d x tilde d is d x tilde times d plus x tilde times d of d plus the quadratic covariation. This is always this is life with Ito. You always have an additional term that comes from the fact that your processes are not absolutely continuous, which is the quadratic variation. And so by definition, you get dx times d. Then you get, because of the definition of x tilde, you see that you have dx plus dx cross d divided by d multiplied by d, so you just get dx cross d. So minus dx cross d plus x tilde d of d plus, now again, the difference between x and x tilde is something absolutely continuous. So this has no effect whatsoever on cross product. Okay, and now you see what is going on. These two cancel out. And you are only left with martingale increments. Okay, because x is a p martingale and d also. Okay, I think I'm now in a position to give you like the last thing that I need about this stochastic localization process. So recall, so f is some test function, and I look at this. Okay, before I do it, just one comment. So, okay, so I'm coming back to my situation, to our situation, so to the localization. So dt was integral exp theta t dot x minus t x square over 2 d mu. I want to call this, to see this as a function of theta and t. So let me call this exp phi of t and theta t, where phi is what it should be. Okay, so phi of t and theta is log integral exp blah 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 d mu. Some sort of log Laplace of mu. So apply Ito's formula to phi t theta t. So recall this is p Brownian motion. So I'll spare you some of the computation, but you will have that the expression for dt is dt times grad phi t theta t d theta t. So Girsanov tells me that x p martingale amounts to x minus integral grad phi no, actually I don't want the general case. Tells us that the process theta, well, I will call it W, given by, okay, dw t is d theta t. Now I want to compensate for the change of measure. So remember the compensation was minus d theta cross d divided by d. And theta is a standard Brownian, so the compensation gives you exactly d theta t minus grad phi of t theta t dt is a q b n. Okay, and now you start to see why I choose this weird notation for a Brownian motion. It's because in the new probability space, the Brownian motion will be this guy and not this. And from now on, I will only live on this new probability space. And now I can state the last thing that I really need about stochastic localization, which is the fact that, so remember that if you start with, so if you have some state test function, this object is a Q martingale. So this is, so covariation, okay. Okay, so you can write it in coordinates. So you have d of d, so this is d times sum di phi d theta I. So d of the quadratic variation between theta so let's, okay, here there is something that is a bit hidden in what I did, is that I wrote Girsanov for some process taking values in R, and here my process takes values in Rn, so I apply it coordinate-wise. Okay. So if I take the quadratic covariation between theta I and d, I will get, so maybe I should have called it J. I will get sum dj phi times the quadratic covariation between theta I and theta j. Okay, but theta is a Brownian motion, and Brownian motion, the coordinates are independent. So the cross covariation are 0. So you only have the term where j is equal to I, and dB, I mean, this is like the most important thing of stochastic calculus is dB times dB is dt. Okay? So you get di phi dt. Okay, so, and here you can think of it as if you apply it coordinate-wise, this means that the quadratic covariation of this vector with this real martingale will be the vector whose coordinates are this guy, which is grad phi. So it's all consistent. It's just Yes, okay. I lost the d here, but somehow here I'm interested in divided by d, so okay, so it was, if you want, it was this. So here, yeah, I was a bit fast, but okay, trust me that this works fine. They can trust me, Bernard? No? Okay. You're okay or pas du tout? Okay. And so it's I apply, if you want, I apply Gersonov to each coordinate of theta. Okay. So this is the new Brownian motion. And now that I have this new Brownian motion, okay, and maybe let me write it here. So you can see that on the probability space, maybe let me put this guy the other side. So you have d theta t, which is dwt plus grad phi t theta t dt. So you see that, so on the new probability space, this is a Brownian motion. So theta solve a stochastic differential equation, a very standard one then. Okay. D theta, some noise plus some function of theta. So this is quite standard. Now the thing is that now that I have this formula, I can give you a formula for this thing which we know is a martingale under the new probability space. Now we can give a formula for the derivative. And this will help us, well, this will be key to understand, to control like everything. So this we already know is a Q martingale. And moreover, the Ito derivative of MT, it has a nice expression. So it's an integral of f, but then you need to like somehow plug in some first moment, like you have some x that appears. And here this AT is the barycenter of mu t. So it's the same AT as before. And the proof that I have done, you know, all these things. So there are, it's like it's really like just some basic Ito calculation, because this MT, okay, so it's I don't know, integral f of x. So there is some like some expression. Okay, let me write. So it's x dot theta t minus tx squared over 2 d mu, and then I have to divide by the integral of that. Sorry? Yes, this is dt, but I want to emphasize here that this is, yeah, this is dt, but I want to write this is the expression for dt. And okay, I'm writing this way because I want to. Here I just want to say that this is some complicated function. This is some function of t and theta t. Where f is what it should be, okay? So by Ito, can say that dmt, so you will have the derivative from that comes from this part. Then you will have the grad f times d theta. And then you will have like the quadratic variation or the ethos term, which is half. And theta on Q, well, whether you're actually, this doesn't depend on the probability space, because whether you are on the first probability space or the second one, like the quadratic covariation of theta has not changed. So this is just Laplacian f dt. So somehow if there is okay, and now I want to work on Q. So this I will replace theta by like I want to introduce like the guy that is a Brownian motion under the new probability space. So I use like the expression that I have for theta. Okay, so this is grad f dw. So this is the martingale increment. Plus dtf plus grad f grad phi. So I'm skipping like I don't put the variables. Plus 1/2 Laplacian f dt. Now, if there is any justice in the world, this should be, this term should be 0. Because I have made everything so that this new process is a martingale, and like the way it's constructed, it should be a martingale with respect. Actually, I know by construction that it is a martingale with respect to W. So in a sense, this proves that this term must be 0. But of course, you can check it directly by putting all. So yeah, I don't have the expression for f, but see it's integral f x blah 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 divided by integral x blah blah blah, and you can check that indeed this vanishes. And so this is 0. And moreover, maybe I can do the computation just of grad f to convince you. So let's compute grad f at t, theta t. Okay, which is grad integral f of x x dot theta minus t x squared over 2 d mu divided by integral x, the same thing, d mu. Okay, let's see. So this is here what I mean grad is grad with respect to the space variable, okay? So this is grad theta if you want. So I need to differentiate this guy and also this guy. Okay? So when I differentiate this guy, so the x will come down from the, so some factor x will go down here, okay? And then I will still have the compensation here. So this will be integral f x times the exponential normalized by the factor here, okay? So this is exactly what I call the d mu t. And then there is another term. The other term, it comes from differentiating this guy. Okay? Okay. So the other term, you will have integral f x blah 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 d mu times integral. So again, I differentiate this guy. So again, there is a x that goes down. X blah 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 d mu. And yeah, if I differentiate, then integral x blah 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 d mu squared, because the derivative of 1 over something is 1 over something squared with a minus. And so if you split like this squared and you give one to this guy and the other one to this guy, you see that this is exactly integral f of x d mu t minus integral f of x d mu t times integral x d mu t. Okay? But x d mu t, I decided that I would call this guy AT. So this is exactly the claim that was over here. Okay? Integral of f. Yeah, I just put this AT inside the integral here. Okay, I will make a short break, but maybe I know it's probably a lot to ingest, but maybe I just make some like takeaway message, and you can run away after and not come back after the break. Is that okay? So I have perturbed my measure by some Gaussian factor. Okay, let me, well, not rewrite everything because it's maybe. Okay, I perturb by something that is Gaussian in such a way that it's a martingale. Okay, no matter how I did this, like forget about it. Okay, the key point is that on average, this random measure is mu. This is the first point. The second point is that almost surely the density of this random measure with respect to mu is some Gaussian where the quadratic term is tx squared. So if mu is log concave, this guy is t uniformly log concave. The second point. And the third point is that when I differentiate, like when I do Ito formula, I have a nice formula for the derivative. Some moment generating formula. So for instance, if I want to compute the derivative of AT, which is integral d mu t, I will get integral x tensor x minus AT d mu t. So each time I differentiate something, I have some moments that appear. So it's a moment generating formula. So this, for instance, this will be, I can call it the covariance of mu t, dwt. So I forgot the dwt. And tomorrow I will have to differentiate, it will get even worse. I will have to differentiate also the covariance. And when you differentiate the covariance, then I will have 3 tensors. So I will have to somehow control 3 tensors. But the message is that when I look at derivative a long time, I have a formula, and I have tensors. And for instance, if you want some hint on what is going on, is that when you're log concave, for instance, you have some inverse order formula for moments. So this will be important. Like I can control moments of order 3 by the moments of order 2. So I will have some differential inequalities for everything. And I will somehow be able to control the way these covariants evolve, for instance, also the way the the barycenter moves around. And this is very important for what I want to do with this. Maybe it's a good point to make a 10 minutes break. I can take questions maybe before, I don't know. There are still questions? Yes?
Just a dumb question. Why is it a covariance since we're only subtracting out the barycenter for one of the x's?
Haha. This is I mean if okay, all I'm saying is this. I mean the other term is 0. So this has nothing to do with yes. Yes.
Is there any connection with the two things?
Okay, I am not very familiar with the paper you're hinting at, so I'm afraid I can't answer.
So you take derivatives of the log Laplace, let's say.
Okay, it's related in the sense that when you take so here I have some log Laplace all over the place, okay? I've perturbed by some Gaussian, and when I take derivative, when you take derivative log Laplace, the first derivative is the barycenter, the second derivative is the covariance. So in that sense, yes, it's related, in the sense that I will have the same type of formula, because I'm derivating log Laplace transforms. On the other hand, as far as I remember, there is nothing random in what they do with this self-concordant barrier. So it's related in the sense that Ronen came up with this by playing around with log Laplace transform, but I don't think that any of the ingredients that they use there is like any of the things that I will do next is present in what they have in the paper, as far as I can tell. But I only remember vaguely what this is about. So yeah, maybe we resume in 10 minutes.